Pluto is relatively far away and dim, a small object in the sky that was once considered part of our solar system. However, recent and surprising announcements by leading space experts Neil deGrasse Tyson and Michio Kaku have brought Pluto back into the spotlight. They suggested that this remote body could possibly be on an imminent crash course with Neptune. They aren't merely hypothesizing, they're issuing a warning. This miniature world may be heading straight for a catastrophic encounter with Neptune. But how could such a thing be feasible? And what would the consequences be if an enormous impact like that truly took place? Are we seeing an odd cosmic illusion, or is something far more tangible and far more alarming speeding through the dangerous path of Pluto toward us? Close to Neptune's orbit, Neil deGrasse Tyson and moreover, Kaku are sounding the alarm. If there's even a slight adjustment, we could be facing a devastating planetary accident. Might Earth be at risk as well? More crucially, how could such a cosmic occurrence even come to pass? Join us as we delve into the possible consequences of a Pluto-Neptune collision. Pluto, once officially a planet but later downgraded to a dwarf planet, still provides intrigue in the vast universe. As demonstrated by current models from leading researchers, Pluto's path passes perilously near Neptune. Renowned scientists Neil deGrasse Tyson and Michio Kaku are both alerting the world to a potential conflict between these two bodies, which could imply a substantial hazard for Earth. Yet how could this scenario unfold? Pluto's journey around the Sun is unlike that of any other body in our solar system. It takes an incredible 248 Earth years to complete one revolution. Since its discovery in 1930, it hasn't even made one full orbit. Still, the intrigue doesn't stop there. Pluto's orbital path is stretched out, a great deal more so than the generally circular paths of the main planets. Even more fascinating is its orbital inclination, a tilt of 17 degrees compared to the Sun's plane. Neptune's actions during this course are far more irregular than those of the other planets, adding layers of complication to Pluto's movement. Arguably, one of the most fascinating aspects of Pluto's route is that it intersects Neptune's orbit for about 20 years in each orbital cycle. Pluto is actually closer to the Sun than Neptune during this period, defying what we'd expect based on their standard positions. This raises the usual question: why haven't they collided? The answer lies in the gravitational effects of nearby giant stars and complex orbital mechanics. The path of Pluto has puzzled astronomers since its discovery. Early observers attempted to make sense of its odd orbit. While most planets follow loops that align with the Sun's plane, Pluto's trajectory is slanted and uneven. The puzzle deepened when scientists realized Pluto's orbit crosses that of Neptune. The stability of Pluto's motion, despite these bizarre characteristics, demonstrates the subtle intricacies of space mechanics. This is where the three-body problem becomes central. Understanding how three celestial objects like Pluto, Neptune, and the Sun influence one another through gravity. It's like predicting future positions based on their initial placements. In Pluto's case, mutual gravitational pulls create complexity in its motion. Pluto, Neptune, and the Sun work in an interlinked system. Terms like asynchronous oscillation, orbital drift, and the VZK wobble are key to decoding this riddle, as highlighted by astrophysics experts. What helps maintain celestial bodies on stable routes is asynchronous oscillation. In Pluto and Neptune's case, this means that when Pluto moves through Neptune's path, it is positioned at least 90 degrees away from Neptune, a safe angular buffer that prevents a crash. Orbital drift, on the other hand, involves the vertical displacement of a body as it circles. For Pluto, this suggests that when it draws near Neptune or another large planet, it is far above their orbital paths, adding another safeguard against potential impacts. Another important factor is the VZK wobble, named after researchers Zell, Kai, and Kaku, who studied the gravitational interactions of space objects. It describes how three massive entities like Pluto, Neptune, and the Sun exert pressure on one another, affecting their actions. In relation to Pluto's situation, the VZK wobble offers insight into why its orbit, even though it appears erratic and unstable, remains relatively smooth over very long periods. This wobble aids in maintaining a stable orbit. Despite the chaotic appearance of space, unpredictable underlying principles still maintain a degree of stability. These forces support Pluto's consistent motion, preventing a Neptune collision. The James Webb Telescope's stunning observations further reinforce this. While deviations exist, this three-body dynamic is vital to understanding how orbits shift due to gravitational interference. Studying it gives us more clarity about Pluto, our planetary group, and even distant galaxies. Computational models from the 1980s indicated that while Pluto's orbit is stabilized by certain features, it still exhibits unpredictability. Minor changes in starting conditions can cause major deviations over centuries. Still, Pluto's orbit has remained steady over remarkably long durations. Modern automated data has allowed us to better observe how the enormous planets, Neptune, Jupiter, and Saturn, influence Pluto's journey around the Sun. Pluto and Neptune share a special orbital rhythm. For every 2 laps Pluto makes, Neptune completes 3. This synchronicity helps preserve Pluto's route. But Neptune isn't the only player. Jupiter's powerful gravity plays a major role in keeping Pluto's path stable. Saturn also contributes. Studies show that Jupiter's mass is sufficient to help maintain Pluto's trajectory for possibly billions of years. It appears that Neptune, Jupiter, and Saturn are collectively working to ensure Pluto travels safely through space, avoiding danger. These unusual but vital systems are necessary for maintaining our solar system stability. Without them, space would be far more chaotic. Objects like Pluto might crash into others or be expelled from the system, creating chain reactions across the cosmos. Particularly in Pluto's case, and concerns about future encounters with Neptune, understanding its movement is essential. This gives us a clearer view of the ever-changing dynamic nature of our planetary family. Pluto's case shows how even seemingly unstable orbits can achieve harmony through complex gravitational and kinetic balances. It also highlights the need for constant observation and analysis of these anomalies to better understand our place in the universe. Exploring the outer realms of space often brings us face to face with the strange nature of celestial phenomena. Pluto's orbit is a perfect representation of such irregularity. The concept of orbital chaos, which refers to how orbits are highly sensitive to their starting conditions, is clearly at play here. For Pluto, this means that even tiny changes in its position or speed can significantly alter its course over time. Using computer simulations has greatly aided scientists in examining Pluto's behavior. These tools use complex formulas to replicate how Pluto and planets like Neptune interact through gravity. By tweaking initial variables, researchers can observe how even minor adjustments may completely change Pluto's destination. Back in the 1980s, digital models unveiled a startling feature of Pluto's orbit. Despite built-in stabilizing factors like asynchronous oscillation and orbital drift, Pluto's journey can still act unpredictably. A slight difference in its starting location or velocity could produce drastically different results in just a few years. Nevertheless, Pluto's path has held steady over billions of years. This indicates that underneath its erratic appearance lies a hidden consistency. Predicting the motion of celestial objects, especially those with erratic orbits like Pluto's, remains an enormous challenge. The inherent instability of such systems makes theories on the object's origin and long-term forecasts loaded with uncertainty. While mathematical models are excellent tools for understanding and predicting space dynamics, they also show our limitations. These calculations heavily rely on precise starting values, and even a small error can lead to drastically different results, making precision very difficult. Beyond the unpredictable nature of orbital paths, Pluto also represents the continual transformation and movement within the cosmos. Despite humanity's considerable achievements in astronomy, Pluto's unusual behavior reminds us how much we've yet to learn. Studying how massive planets shape Pluto's movement helps us better comprehend the dynamics of the solar system. It shows that each planet's mass and location can significantly influence others. So why are high-profile astrophysicists suddenly worried about a potential Pluto-Neptune impact, despite all the cosmic mechanisms designed to avoid it? Neil deGrasse Tyson, a celebrated scientist and leading voice in public astronomy, offers a unique take on our planetary puzzles, especially Pluto's unusual story. Tyson, known for advocating Pluto's reclassification as a dwarf planet, provides insightful commentary on how our understanding of orbits and the evolution of the solar system has changed over time. He doesn't see the change in Pluto's status as disrespectful, but rather as a necessary correction based on expanding scientific knowledge. Tyson believes that learning and adaptation are central to grasping complex orbits. He views trajectories like Pluto's as an indication of how much more there is to discover. The wonder behind such mysteries keeps astronomy exciting. Yet while Tyson is generally optimistic, his view of a potential Pluto-Neptune collision is far more sobering. His concern about Pluto's fate, once an official planet, stems from his awareness of orbital instability. He acknowledges that Pluto has stayed safe so far, but even tiny changes accumulating over time could lead to disaster. Pluto's orbit, especially its overlapping section with Neptune, forms a fragile cosmic rhythm that may not last forever. Tyson argues that even minor shifts in Pluto's movement could lead to major consequences over thousands or millions of years. Such disturbances could cause chaos, or even a direct collision. Though this is not an immediate threat, it's a possibility unfolding on a timescale far beyond human civilization. Still, Tyson's cautious tone stresses the importance of maintaining constant vigilance and further study of Pluto's orbit. Tyson isn't alone. Michio Kaku, a world-renowned theoretical physicist, also sees the possible mayhem that might result from planetary interactions. Like Tyson, Kaku is amazed by the universe's vastness, but he also understands the fragile balance of planetary systems and the unpredictable outcomes that may arise. Both Kaku and Tyson emphasize the importance of relentless exploration into the invisible forces guiding orbital paths and the long-term future of our solar family. In conclusion, Pluto's circumstances reflect how our knowledge of the universe is in constant motion. Each discovery opens new questions. As astronomy advances, the slight chance of a Pluto-Neptune impact serves as a humbling reminder. The universe is full of surprises, and even seemingly peaceful planetary paths can change significantly over time. Pluto's lessons inspire us to keep looking up, and to keep wondering what secrets the stars have yet to reveal.